So this will be the end of section 5.6. It's part 2. And if you didn't look at the problems, and if you just looked at the instructions, it's going to look a lot the same. The instructions for 21 through 32 are the same as the instructions from 1 through 8. It says find where f of x is bigger than 0 and where f of x is less than 0. But instead of giving us a graph, they give us a function. And all we're going to do is we're going to sketch a graph of that function. We're going to mark the x-intercepts on the x-axis. We're going to mark the x-coordinates of any vertical asymptotes on the x-axis. And then we're going to answer the questions exactly the same way. I made a little note to myself that I thought I would say. So algebraically, before I jump into the graph, I'm going to find the x-coordinates of all x-intercepts and vertical asymptotes, plot those on a number line or on my axis, create intervals. Then I'm going to insert the graph of the function, and then I'm going to figure out where the graph is beneath and above the x-axis real quickly. So for problem 22, if I want to find out where the f of x's are greater than or less than 0, I need to know the x-coordinate of any x-intercept and the x-coordinate of any vertical asymptote. We only get vertical asymptotes where there's fractions, so I just really need to find the x-coordinate of the x-intercepts. So I'm going to do the algebra necessary to find the x-intercepts by setting the function, the right-hand side of the function, equal to 0. And to do that, I'm going to factor. That's going to factor into x plus 5 times x minus 1. And I'll get x equal to negative 5 and x equal to positive 1. So when I go to do problem 22, I'm going to need to put negative 5 on the x-axis, positive 1 on the x-axis, and negative and positive infinity. And I'm going to create intervals. The intervals are going to have all round brackets because I don't have any or equal to's. The intervals are going to be negative infinity to negative 5, and then negative 5 to 1, and then 1 to infinity. Now I'm going to sketch a graph of this function, x squared plus 4x minus 5, doing a zoom standard. And I'm going to insert that graph to the on this picture that I started. So I'm going to do x squared plus 4x minus 5, zoom standard just in case I have some strange window. There's my x-intercept at negative 5. There's my x-intercept at 1. So the graph looks something like this. I don't need to know where the vertex of that parabola is. The graph looks more or less like that. Now I should be able to answer the question exactly the same way that I did the first 20 problems, actually. So when I go to do part 22a, the regions that are going to be above the x-axis where the y's are positive would be that region and that region, because that corresponds to those two parts. So 22a is going to have the intervals from negative infinity to negative 5 and positive 1 to infinity. 22b wants the region where the graph is beneath the x-axis. That's going to be that portion of the graph which corresponds to the interval negative 5 to 1. So there's just a little bit extra we have to do for these problems, specifically finding the x-intercepts and any vertical asymptotes, and then just get a graph from your calculator. I don't have to be really picky about my window, but there might be a time where the standard window is not helping me, and I'll tweak it a little bit. So your 21 should solve just the same way. When we go to do 23 and 24, I'm going to start off doing 24, finding the x-intercepts. It's not a fraction, so there's no vertical asymptote. So the beginning of my problem 24 is I need to find the x-coordinates of the x-intercepts and plug those on the x-axis, or plot those on the x-axis. And I'm going to solve this by factoring. My problem 24 factors just like your problem 23 factors. Mine factors into 4 plus x times 4 minus x equal to 0. So I'm not spending a lot of time talking about factoring. Hopefully your factoring skills are decent. Once I have it factored, I can split it up and set each factor equal to 0. For this one to solve it, I'm going to minus 4 from both sides and get x equal to negative 4. For that one, I'm going to add x to both sides and get 4 equal to x. So on my x-axis, I need to plot negative 4 and positive 4 real loosely. I don't have to really get that accurate with my graph. I also need to plot the infinities. The intervals are going to be called out are the interval from negative infinity to negative 4, the interval from negative 4 to 4, and the interval from 4 to infinity. All round brackets because neither one of these have an or equal to. If I had an or equal to in the questions, the x-intercepts would get square brackets. Now I'm going to graph the function 16 minus x squared. And when I do this, I'm not going to see so great the vertex. If that bugs you, we can make the vertex show up. It doesn't bug me that the vertex, I know the vertex is up here somewhere. So when I copy my graph, I'm going to make sure that it goes through the x-intercept at negative 4, the x-intercept at positive 4, and it goes up high. I don't really care how high it goes up, but the graph looks something like this. I knew it was a parabola because it had an x squared. If you wanted to see the top of the vertex, you need to make the y max bigger than 16. If I made the y max at 20, then you'd see the whole parabola. If it doesn't bug you that you didn't see the whole parabola, then you could sketch something and it would be accurate enough because no portion of the graph up there is going to switch beneath the x-axis. It's all above the x-axis. So when I go to answer my 24 part A, I need the regions that are above the x-axis, which would be that region and that region. So I'm going to put the intervals from negative infinity to negative 4 and the interval from 4 to infinity. And for part, whoops, that's wrong. Those are the, whoa. I tried to go too fast and it didn't work so well. The interval of negative infinity to negative 4, it actually corresponds to that portion of the graph. That portion's beneath the x-axis. Let me just destroy all this. Oh, sorry about that. And the interval from 4 to infinity represents that portion of the graph. Sorry, I started making a mistake there. The interval from negative 4 to 4 actually corresponds to the portion of the graph that I just pointed at. So this was a bad pointing job. The first interval, negative infinity to negative 4, corresponds to that interval. It's beneath the x-axis. So as I go to answer 24, part A wants the regions above the x-axis, and part B wants the regions beneath the x-axis. That region, negative infinity to negative 4, is beneath the x-axis. The next region is above the x-axis, so it goes in part A. And the last interval is beneath the x-axis. It goes in part B. It's beneath the x-axis, so the y's are negative. It's above the x-axis, so the y's are positive, essentially. So apparently you can't just rush through these so quickly, because when you rush through them, you can make mistakes. So let me slow down a little bit here. Move on to 26. 26 says, use synthetic division if you care to, or use a table feature on your calculator to find the x-intercepts. So to find these x-intercepts, I'm going to need a graph. Let me graph the function in problem 26. So f of x equals x up arrow cubed plus 7x squared minus 4x minus 28. I don't know how well I'm going to see the graph with this window. If it bugs you, the graph shoots off the screen. I need to make the y-maxes higher to see the top of the graph, and I need to make the y-mins lower to see the bottom of the graph. I don't really need to see the top and the bottom of the graph, but if it bugs you that I can't see them, change your y-maxes and y-mins to some big numbers like 50s. And I think when I hit graph now, I should be able to see the top of the graph and the bottom of the graph. So when you can't see the turning points, just change your y's. If you can't see the top turning point, make the y-max bigger. If you can't see the bottom turning point, make the y-min lower. So this is a graph. I need to know the x-intercepts, and synthetic division is one way to get the x-intercepts. Another way to safely get the x-intercepts is to hit second in table, and any point in the table that has a 0 on the y is an x-intercept. So one of the x-intercepts is going to be negative 2. A second one of the x-intercepts is going to be positive 2. And the third x-intercept, well, I don't see it. Look at that graph. There's negative 2, there's positive 2. The other x-intercept is like negative, less than negative 2. Let me go back to my table and go back the other way. So there's my -2 and 2, and the one that I was missing is this -7. So the x-intercepts, if I look at the graph, that's at -7, this is at -2, and that's at +2. Let me put those on an axis real quickly. So on my axes, I'm going to put -7, -2, +2, positive and negative infinity. The intervals I'm going to create are -infinity to -7, -7 to -2, -2 to +2, and +2 to infinity. There aren't any vertical asymptotes to worry about. Then I'm going to just kind of shove this graph on there. The graph goes through the x-intercept at -7, up to a turning point that I don't need to know, back down to the x-intercept at -2, through a turning point that I don't need to know, and then it passes through the x-intercept at 2. So that's a reasonable graph. Now I need to figure out how the intervals break up. The first interval corresponds to that portion of the graph which is beneath the x-axis, so it goes in part B. So part of my answer to 26B is going to have the interval from -infinity to -7. The next interval corresponds to this region, which is that region, and that's above the x-axis. The y's are positive. That goes into part A. The third interval corresponds to this region where the y's are negative and the graph is beneath the x-axis, so that goes in part B. And the last interval corresponds to that region where the graph is above the x-axis, so that goes in part A. Your 25 should work real similarly. For 28, it doesn't tell me I could use my calculator to find the x-intercepts, but I'm going to do it anyways. I don't know if it's cheating, but I'm going to use my calculator to find the x-intercepts. So I'm going to graph problem 28, which is x up arrow 3 plus 4x squared minus 5x. I'm going to graph it. I have that bizarre window, and that window, and it's not so great there. Let me go back to a standard window. Go back to zoom standard and see if I could see better what I need to see. Well, I can see this part very well, but not that part. To see that top up there that I was able to see before, I'd have to make my y max higher. That point right there is going to start to disappear on me as I make the y max lower. Let me find the x-intercepts real quickly and then play with the window. So second table, there should be 3 x-intercepts because this graph crosses the x-axis 3 times. First time is at -5. Second time is at 0. And the third time is at 1. So on my graph, I need to mark -5, 0, and 1. Also the negative and positive infinity. I'm going to create intervals from -infinity to -5, from -5 to 0, from 0 to 1, and from 1 to infinity. And then if I need to see a better graph than I have, I can change the y max. So hit the window and make the y max a little bit higher, maybe like 25. And then you'll start to see the graph better. So the graph looks something like this. It's beneath the x-axis. It goes through the x-intercept and goes above the x-axis. Hits its turning point that I don't need to know. Comes back down, goes through the x-intercept at 0. Dips beneath the x-axis and goes back up, goes through the x-intercept at 1. So that's kind of what my calculator gave me. I don't need to be that accurate as I sketch my graph. Just have to get the portions above and beneath the x-axis proper. The first interval corresponds to that region that's beneath the x-axis. So as I go to answer this, that's going to go in part 28b. All round parentheses here because I don't have an or equal to in the problem. The next region corresponds to that portion of the graph. It's above the x-axis, so that goes in part A. The third region corresponds to this portion of the graph, which is beneath the x-axis, so it goes in part B. And the last region corresponds to that portion of the graph. It's above the x-axis, so I get a part A. All right, so you should be able to do 27 similarly. The next problems are fractions. Fractions, I have to worry about vertical asymptotes. For the fractions, I need to plot the x-intercept and the x-coordinate of the vertical asymptote on my x-axis. To get the x-coordinate of the x-intercept, the slick way to do it is just to set the numerator equal to 0. To get the x-coordinate of the vertical asymptotes, you set the denominator equal to 0. So the numbers I'm going to plug on my x-axis are x equal to -5, which is the x-coordinate of the x-intercept, and x equal to 6, which is the x-coordinate of the vertical asymptote. When I go to sketch a graph, I need to have -5 marked, which is an x-intercept, +6 marked, which is going to be a vertical asymptote. The intervals I'm going to create are -∞ to -5, -5 to +6, +6 to infinity, all round brackets because neither of the problems ask for an or equal to. If there was an or equal to, the vertical asymptote would still get a round bracket, but the x-intercept would get a square bracket. Let me graph this with a standard window, and hopefully I can see everything I need to see. So I'm going to graph the function, parentheses x plus 5 divided by parentheses x minus 6. And I'm just going to do zoom standard. It's not going to graph the vertical asymptote. If I want the vertical asymptote graphed in, I can do that. To graph the vertical asymptote, I'd go y equals 1,000 times x minus 6. There's the vertical asymptote. This part, if it bugs you, you can make the window smaller. As you make the window smaller, you're going to lose this portion of the graph. So let me insert that portion of the graph here. And then if I want to see this portion of the graph better, I need to make the y's smaller. If I made the y's go like from -3 to 3, I'm going to lose this portion of the graph, but I'll see better what's happening around the x-intercept. So at that x-intercept of -5, the graph crosses the x-axis, and it's above the x-axis in this interval, and then it dips beneath, and it just wanders over towards that vertical asymptote. So the graph looks more or less like that. Go back to a standard window. And now I'm going to answer my questions, at least the best I can. So the first interval, the graph corresponds to that. It's above the x-axis, so that's going to go for part A. So for 30A, I'm going to include the interval from -∞ to -5. The next interval, -5 to 6, corresponds to this portion of the graph where it's beneath the x-axis, so the y's are negative. That's going to go in part B. And the last interval, 6 to infinity, corresponds to this portion of the graph. The graph is above the x-axis, so the y's are positive, so that goes in the interval from 6 to infinity. That goes in the interval from part A. All right, so 29 should work similarly. 32 is a mess, as is 31. Let me do 31 just in case the window's bizarre. So I'm going to do 31 just to help you out here. So for 31, to find the x-intercept, you set the numerator of the fraction equal to 0. You're going to get x equal to 5. To find the vertical asymptote, you set the denominator equal to 0. And this one, when I set it equal to 0, I need to solve by factoring. And you get x equal to -2 and x equal to 2. So graphically, I'm going to have an vertical asymptote at +2, a vertical asymptote at -2, and an x-intercept at 5. The intervals that I'm going to get are -∞ to -2, -2 to 2, +2 to 5, and +5 to infinity. I got lazy, didn't write the infinities on my axes, but I kind of knew that they were going to be there. If I want to graph the vertical asymptotes in y2, I can do 1,000 times x plus 2, and in y3, I can do 1,000 times x minus 2 to get those vertical asymptotes of 2 and -2. And I'm also going to graph the function in y1. So I'm going to do multiple graphs here. So I'm going to clear out the junk and do x minus 5 divided by and then the whole denominator needs to be in a parentheses. So that's the function that I need to worry about. But if I want to get the vertical asymptotes in there because they help me out, I'm going to just get them in there to help myself out. I'm going to go back to a zoom standard. I don't know if that window is going to work so well, but I'm going to hope it does. And I think it does just fine. For the first interval, the graph is in the bottom left-hand corner, and it can't cross the x-axis because there's no x-intercept. So the graph starts beneath the x-axis. It can't go above the x-axis. It just hovers to the asymptote. So the far left looks like that. And again, the graph can't cross the x-axis because there's no x-intercept there. The middle region is kind of this parabola. It looks like this. The graph can't cross the x-axis because there's no x-intercept. The far interval, the graph starts beneath the x-intercept. It gets to the x-intercept. You can't even see it here. I'll fix this window in a bit. But when it gets to the x-intercept, because the x-intercept has odd multiplicity, it's going to cross the x-axis and stay going up. To see better what's happening at the x-intercept, I have to really make the y's really small. And when I make the y's really small, I'll lose some of this detail. But let me show you better what's happening right there by making my window small. Maybe making my y's from -1 to 1. And then you're going to lose all this, or lose a lot of this. But you can see the graph comes up and crosses the x-axis. If I make the window even smaller, like make my y's like -0.25 to +0.25, you'll even see better what's happening at the x-intercept, but you'll lose more and more of the rest of the features. But at 5, the graph crosses the x-axis, as opposed to reflecting off the x-axis because the multiplicity is odd. So now I'm going to answer my questions. As I go to do part 31A, I need the regions above the x-axis, and for 31B, I need beneath the x-axis. The first region is that, and that's beneath the x-axis, so that goes in part B. The middle region is this parabola, which is above the x-axis, so that goes in part A. The third bit is for that region, which is beneath the x-axis, so that goes in part B. And the last region is the portion above the x-axis, which goes in part A. So the next group of problems takes us to 42, which takes us to the end of the section. And the only difference is we now start having or equal to's. For or equal to's, x-intercepts will get the square brackets because the y's are allowed to equal 0 now. But the vertical asymptotes will still get round brackets. And the vertical asymptotes only matter when we're dealing with fractions. I'm going to start off finding the x-intercepts. I'm going to find the x-intercepts by setting the function equal to 0. I'm going to solve this by factoring because it's easy to factor. I factor out a common factor of an x. I'll set the factor of x equal to 0, which will give me an x-intercept that has an x-coordinate of 0, and set the factor of x minus 3 equal to 0, which will give me an x-coordinate of an x-intercept of 3. So on my x-axis, I'm going to plot 0 and 3 along with negative and positive infinity. Start worrying about square brackets. X-intercepts get square intervals here. So I'm going to go interval from negative infinity to 0, square bracket on the 0. Interval from 0 to 3, double square brackets for both the x-intercepts. And 3 to infinity. And then I'm going to graph my x squared minus 3x with a standard window and see what I get here. So y equals, clear out all the stuff from the last problem, and do x squared minus 3x, zoom standard, because a standard window is generally the way to go. I can see everything I need to see. There's the x-intercept at 0. There's the x-intercept at 3. The graph looks something like that. Now when I go to answer part 34A and 34B, I'm just looking for the regions above and beneath the x-axis. 34A corresponds, the first interval corresponds to that portion of the graph which is above the x-axis, so that goes in part A. The middle interval corresponds to this portion of the graph which is beneath the x-axis, so that goes in part B. And the last interval corresponds to this portion of the graph, which is above the x-axis or touching the x-axis for the x-intercept, and that corresponds to 3 to infinity. I don't worry so much about the touching the x-axis. That comes up with the square brackets, and I put the square brackets on my x-intercepts. 35 and 36 are a little evil. When I go to do 36, to find the x-intercepts, you set the function equal to 0. I'm going to write it without that square. To find my x-intercepts, I'm going to write this as x minus 4 times x minus 4. And I'm only going to get one x-intercept. It has even multiplicity, which is one of the horrible ones where the graph kind of bounces off the x-axis. When I go to sketch my graph, the only number other than the infinities I need is the 4. And the 4 is going to be a turning point in some sense. The graph is going to bounce off the x-axis here. And it's the strange answers that I probably would never put on a test, but let me just do this real quickly. So let me graph the function y equals parentheses x minus 4 squared, graph it, and the graph looks something like this. It goes, bounces off the x-intercept at 4, and the graph is always above or touching the x-axis. Both of these intervals, the graph is above the x-axis or has an x-intercept there. Both intervals go in part A. When I go to answer 36a, I get both intervals, negative infinity to positive 4 and positive 4 to infinity. Anytime you have two intervals with the same starting and ending point, if that starting and ending point's in a square bracket, you can slice that out and connect them into one big interval. This is a completely fine answer. It's actually equal to that. That's for 36a. For part B of 36, I'm only looking at the point 4 because that point 4 has a y-coordinate of 0 because it's on the x-axis. It's y-coordinate of 0. There's no points on the graph. There's no intervals on the graph that are beneath the x-axis. There's no y's that are less than 0. But the single solitary point 4, 0 has an x-coordinate equal to 0, and that's the single point that's going to go in my answer to part B. 35 should work real similarly. For 37 and 38, I'm going to find my x-intercepts by setting the function equal to 0. I'll do 38. For 38, I'm going to rewrite the problem without the exponent as I'm finding the x-intercepts. Once I have it all kind of stretched out, I'm going to set every factor equal to 0. I'm going to get x-intercepts at x equal to negative 2 and at x equal to 6. And that x equal to 6 is going to be that single point for one of the answers. So on my x-axis, I'm going to need negative 2, positive 6, along with the infinities. I'm going to create intervals, negative infinity to negative 2, negative 2 to 6, and 6 to infinity. I'm going to graph this function. I might have to play with the window to see the tops and the bottoms of the turning points. If it doesn't bother you that you can't see the tops and the bottoms of the turning point, then you don't have to play with the window. But I'm going to enter the function x plus 2 times x minus 6 squared, hit my graph. The only thing I can't see is a point that's way, way up here. If I want to see that point, I'm going to make my y max extremely large, maybe like 50. And even at that, I can't see the top of that point. So my y max has to be even harder. The x-intercept at negative 2 and positive 6 is here. The graph crosses the x-axis at negative 2, but bounces off the x-axis at 6. Let me make my y max even higher, maybe 100. Finally can see it. So that's the graph that I'm going to copy on here. It starts beneath the x-axis, goes through the x-intercept, keeps going up, gets to the turning point that I don't need to know, comes back down, hits the x-intercept because it has even multiplicity. The graph touches but doesn't cross the x-axis and bounces back up. So now for my first interval, the interval from negative infinity to negative 2, it corresponds to that region. The graph is beneath the x-axis, so that goes in part B. So for 38 Part B, I'm going to put the interval from negative infinity to negative 2. The next interval, negative 2 to negative 6, corresponds to positive 6, corresponds to that region. It's above the x-axis, so it goes in part A. So part of the answer to part A is the interval from negative 2 to positive 6. The next region, again, is above the x-axis. That corresponds to 6 to infinity. That's going to go in the answer to part A. This single point here is the point 6, 0. Because it's y equals to 0, it needs to also go in part B. Part B wants any points that have y's beneath or touching the x-axis. There's no point in this interval beneath the x-axis, but that point's touching the x-axis. That 6 should go in my answer to part B. This is a completely fine answer to this problem. These two intervals, because they're two intervals with the same ending and starting point connected in square brackets, could be condensed to a single interval. And that interval would be negative 2 to infinity, just including the starting point of the left one and the ending point of the right one. But if you just gave me this interval for part A, it's completely fine. You need all this for part B because that turning point has a y-coordinate equal to 0 and it needs to be in that answer. Your 37 should work the same way. We just have 2 problems left to do. And for these fraction problems, the x-intercepts get square brackets, the vertical asymptote gets round brackets. To find the x-intercept, you set the numerator equal to 0. In my problem 40, my x-intercept is going to have an x-coordinate of negative 4. I'm going to plot that on my x-axis and put a square bracket there. To get the vertical asymptote, you set the denominator equal to 0. And I'm going to put a round bracket there. So when I go to mark up my graph, at negative 4, I'm going to have an x-intercept. At positive 6, I'm going to have a vertical asymptote. The vertical asymptote is going to get a round bracket. The x-intercept is going to get a square bracket. The intervals I'm going to create are negative infinity to negative 4, square bracket on the x-intercept. Negative 4 to 6, square bracket on the x-intercept, round bracket on the vertical asymptote. And 6 to infinity, round bracket on the vertical asymptote. I'm going to graph this with a zoom standard. I don't know if the zoom standard is going to be the best window, but I'll play if I have to. So now zoom standard. I can see this region really well here, so I'm just going to copy this in. I can't see so well what happens at the x-intercept. I can see over here the graph goes kind of like that. I didn't draw the vertical asymptote in. Let me get it in there by doing 1,000 times x minus 6. 1,000 times the factor that gave that x-intercept will graph that vertical asymptote. So I have this portion of the graph. I know that the graph jumps above the x-axis here. This is not a turning point because that has odd multiplicity. If you want to see what's happening better around this x-intercept, you have to make the y-min and the y-max really small, which will make you lose this portion, but I have that drawn in already, so I don't mind that. So if I make my y-min like negative 0.25 and my y-max positive 0.25, I'll see better what happens at the x-intercept, really extremely better. At the x-intercept of negative 4, the graph crosses the x-axis and doesn't come back down. We'll go back to my zoom standard. And now I'll answer the questions. The first interval, negative infinity to negative 4, corresponds to that portion of the graph that's above the x-axis. So that's going to go as part of 40a. So I'm going to get negative infinity to negative 4 as part of 40a. The next interval, negative 4 to 6, corresponds to that portion which is beneath the x-axis. So that's going to go in part B. Square bracket on the negative 4, round bracket on the 6. The last interval corresponds to that portion of the graph which is above the x-axis. It's going to go in my answer to 40a. One more problem for me to do. If you've done 39, then just one more for you. Let me do 41 just so we finish up your homework nicely. So for 41, to find the x-intercept, you set the numerator equal to 0. So I'll go x plus 6 equal to 0 and get x equal to negative 6. That's going to be a square bracket. I'm going to get 2 vertical asymptotes. I'm going to set the denominator equal to 0. I'm going to factor this. And get x equal to negative 3 and x equal to 3. So when I ultimately do a graph, I'm going to have negative 6, which is a vertical asymptote, which is a square bracket. Negative 3, which is a vertical asymptote, which is a round bracket. Positive 3, which is a vertical asymptote, which is a round bracket. The intervals I'm going to have are negative infinity to negative 6. Infinities always get round brackets. The numbers gets x-intercepts get square brackets when the question has 0 or equal to. Middle interval, negative 3 to 3. Vertical asymptotes always get round brackets, and then 3 to infinity. To graph the vertical asymptotes in y2, I'm going to do 1,000 times x plus 3, and in y3, I'm going to do 1,000 times x minus 3 to get these vertical asymptotes drawn if you need to see them. So now I'm going to graph the function in problem 41 with a standard window. I'm going to do x plus 6 divided by parentheses x squared minus 9, and then get my vertical asymptotes in of 1,000 times x plus 3, which just kind of simulates the vertical asymptote, and 1,000 times x minus 3. Go back to a zoom standard because I don't have a better starting guess. And then the only place the graph can cross the x-axis is at that point right there. So this middle region, oh, that's a bad window. Let me really crunch my y's down. Let me make my windows go maybe from negative 2 to 2 on your y's. And that's going to give me probably a better looking graph. So the middle region looks something like this. The upper right region looks something like this. And the upper left region is the only region where the graph can cross the x-axis, because it only can cross the x-axis at an x-intercept. The x-intercept has odd multiplicity, so the graph passes through the x-axis as opposed to dipping under the x-axis. To see better what happens at that x-intercept, I'd have to make my y's really small, like negative 0.25 to positive 0.25, and you start to lose that part of the graph when you do that. But at that small window, you can see what I drew in there is really representative of what happens. Now when I go to answer this, for 41a, I need the regions above the x-axis. That's this region right here. And I missed an interval. I missed the interval from negative 6 to negative 3. I'll be darned. We'll even see it there. Negative 6 to negative 3. I missed that interval, but this is the interval right here. This interval right there corresponds to negative 6 to negative 3, which is above the x-axis. It goes in a part A. The other interval where the graph is above the x-axis is that interval, which is the 3 to infinity. So the answer to part A is going to have those two intervals. My answer to part B needs the regions where the graph is beneath the x-axis. This interval right here, the graph is beneath the x-axis. That corresponds to negative infinity to negative 6. And that region right there, which corresponds to negative 3 to 3, the graph is also beneath the x-axis. So hopefully this was a friendly-ish repetitive section. And so we're done with Chapter 5 other than the review. So if you can do all the problems on the review that comes up next, you'll be perfectly prepared for the test.